Hello students, this is Mr. Ezra. Today we are going to talk about characteristics of radical functions. We're going to start with the parent function f of x equals the square root of x. The first thing we want to do is to get this function on a graph. So I'm going to pull up my graphing calculator and review how to do that. So once you get your graphing calculator out, you want to go to y equals. It's right here in the top left. And you're going to type in the square root of x. So you hit a second x squared to get square root. Your X button is this variable button right here. It's got several different variables, but it only pops up an X. And it's always a good idea to close the parentheses after when you're ending a square root. So we've got the square root of X here. Y sub 1 equals the square root of X. Now, if you want to take a look at what the graph looks like, a very good zoom is to choose zoom standard, number 6. Zoom standard goes from -10 to +10 in both directions. You'll notice the graph we have provided on the right does the same thing. So this, once we get our picture on the right, it should look kind of like this guy here. And you'll notice with the square root function again that it kind of starts in the middle at the origin and kind of increases to the right forever from there. If you want to play with the window, you can always change the view by changing your X max and min and your y min and max, which basically gives you the ability to, instead of from 10 to -10 to +10, to change it from like -2 to +10, or really whatever you want. You can change either axis that way. I'm interested today, instead of looking at just the graph, in looking at the table of values. So I hit second graph to get to those tables. Now this table tells you some things. It tells you that at -10, -9, all the way to -4 at least, there's an error message in the output. Why is that happening? Well, remember, we cannot take the square root of a negative number without an imaginary or complex number, and the coordinate plane does not graph those types of numbers. So the first time that we get an actual number that we can use is 0, 0, and you just want to arrow up or down and get a handful of these points to graph on the graph. I've already done this for us. Here is a list of coordinates from 0, 0 up through 11, 3.3. Now we don't have to graph every single one of these, but if we start at our starting point of 0, 0, and we go 1, 1, 2, 1.4, it's about right there. I have to kind of guess where that is. 3, 1.7, a little higher up. 4, 2. Now remember, that's 4, 2 because the square root of 4 is 2. In fact, if you don't have a graphing calculator, you have to plug several of these numbers in for x to a non-graphing calculator to get the outputs, which should be similar to these decimals and these integers here, and use those. So you have to make your own XY list if you don't have a graphing calculator to do it for you. So let's see, our next one is 5, 2.3, 6, 2.4, 7, 2.6. Now, do I have to get every single one of these dots on here? No, I mean, I can skip around. As long as I get 3, 4, 5 of them on the graph, that should be good enough for me to get the shape of the picture, to get an idea of what it's looking like. So we can see that as we're going up through here, it's just basically going to continue to increase kind of slowly forever and ever. So let's see if we can get that picture going. Whoops. So we're going to go up. Then it's going to start to kind of curve this way. And it would continue to increase forever and ever. No matter what x value I plug in, as long as it's positive, I'm going to get an output on this function. So I have a starting point at 0, 0, and it goes forever to the right. Now, when we talked about transformations, we talked about how the function shifts up, down, left, right. And this function is a parent function. It doesn't shift any direction, and its starting point is always going to be 0, 0, or the origin. And while this function increases forever, it doesn't increase forever from left to right. There's a starting x value where it begins to increase, and that starting x value is at 0. 0 is the furthest to the left that this function goes, and that 0 is our starting point for our interval of increase. We're going to remember, we only use x values, so an x value of 0, and it increases forever and ever and ever towards positive infinity. There's only one interval on this function, an interval of increase. There's no interval of decrease for this function. The domain is not all real numbers, and this is the first function that we've looked at this year where the domain wasn't all real numbers. This domain has a starting or lowest x value of 0, and and of course it increases forever to the right towards infinity. You'll notice that the domain and the interval of increase are the same, except we're going to put a bracket on the 0 for the domain because that point is included as part of the function. The square root of 0 is 0. 0, comma 0 is on this function. So we want to make sure we show that the 0 is included by putting brackets around it. For the range, we're going to do kind of a similar thing. So we've got our lowest y value is also 0, and it's included in the range, and it increases forever and ever up towards positive infinity. The domain and range are not always the same for functions like this, but for this parent function, they end up being the same in this case. Now, do we have an absolute max here? Well, if a function increases forever and ever up, there is no absolute max. It's not possible, right? We have to have a highest point on the function, and if the function increases forever towards positive infinity, that doesn't happen. But what we do have here is an absolute minimum at 0, comma 0. This is the lowest point on the function. So we can say that there is an absolute minimum at 0, comma 0. Within behavior, this is going to be a little different than the functions we've looked at up to this point. Okay, we're going to kind of start filling this in ourselves, so a little bit more of it than we have in the past. Let's start with the left side, and then we'll plug in the right side. Now, the question you have to ask yourself is, as I travel along this function to the left, as I'm going to the left, as I'm going to the left, do I approach a point or do I approach an arrow? If you approach a point, if you get closer and closer to a point, well, the x value of that point is what you want to put. So for the end behavior on the left end, we're approaching an x value of 0, and that point has a y value of 0 as well. So as x approaches 0 towards the left, your function approaches 0 from above. On the right side, so we're kind of at a different part of this now. On the right side, we're going to the right forever and up forever. Well, to the right forever is towards positive infinity, and up forever is towards positive infinity. So this kind of looks a little different than in behavior that we've seen before. We've got to kind of get used to thinking, am I approaching a point or am I approaching an infinity? Let's take a look at another example. Now, rather than getting the graphing calculator every time and kind of re-putting things in, I've already done that for us. I've already got a list of x and y values for us to graph. Remember, this is a square root function, and it's been transformed, and there are some transformations that we should probably know by now without even putting anything on a graph. Remember that if there is a number at the very beginning, before we even get inside the radical, that is going to be a vertical stretch. And that vertical stretch here is by a factor of 2. Well, that means that any point that was on the parent function is going to have a distance that is twice that from the x-axis as the original parent function's point. We see also a negative in front of the x underneath the square root sign, and we need to be comfortable with the fact that that is a reflection, but we've got to remember which axis it reflects over. And in this case, remember, why am I in here? A negative inside the radical is a reflection across the y-axis. And finally, we have -3 at the end. That's our third transformation here. Remember, when you are outside of the square root, those are transformations that are in the up or down or vertical direction. So -3 is a shift down 3. What we should notice when we start plotting these points is that this function should reflect across the y-axis. So instead of increasing to the right, it should increase to the left. It should stretch by 2, so it should be a little bit more stretched out away from the y-axis, and it should shift down 3 points, which basically means that starting point, instead of being the origin, should be down at 0, -3. That's where my function should start since I shifted down from the origin 3. I'm going to use these xy point values, these xy values from my graphing calculator to get some points on here. Let's see, we'll do negative 10 comma 3.3. 3.3 is about right there. We'll do negative 9.3. Skip over to negative 7 comma 2.2. Let's see, how about negative 4 comma 1? See, I'm not getting every single one of them, but I want enough so that I can see what's going on. Maybe negative 2 comma negative 0.17. So we're here is about where we're crossing the x-axis. And then negative 1 comma 1 and 0 comma negative 3. So you can see that this is our starting point because we shifted down, but instead of increasing to the right, since we're reflected across the y-axis, we're increasing to the left. We've got to connect the dots through that increase to the left. And you should notice that compared to the function that we just graphed, that this one is a little bit more stretched out. So where is our starting point? We shifted down 3. Our starting point is at 0 comma negative 3. Remember with increase or decrease, you have to think left to right. Are we going uphill or downhill from left to right? Well, this is downhill from left to right, so this would be considered decreasing and not increasing. And we are decreasing forever from negative infinity to this x value right here of 0. So we're forever decreasing from negative infinity to 0. Intervals of increase and decrease never get brackets, they only get parentheses. The domain and range with this type of function will get a bracket somewhere. As we describe the domain, we're going to understand, I guess, eventually that our domain is the same as the interval of decrease here. We're going from negative infinity. We have x values on this function from negative infinity all the way to an x value of 0 on the right side, and that 0 is included, so it gets a bracket. Our range, we have y values. Remember, range is bottom to top. Whenever you think about range, you got to start at the lowest point. Our lowest y value is negative 3. And we have y values forever on this function. As I go up the y-axis, I have a y value on the function. I have a y value on the function. As high as I go on this axis, there's a value, there's a point on the function somewhere that has that y value. So up towards infinity, positive infinity. I know it's increasing to the left, but we're talking about all these y values that get higher and higher as we go up the graph. There are coordinates on this function that have those y values. All right, do we have an absolute max or min? Well, since there is a lowest point, that means our minimum is an absolute minimum at 0 comma negative 3. All right, in behavior again. Again, I would like for you to break your picture into a left side and a right side. And I want you to describe what's happening on both of those sides. On the left side of this function, on the left end of this function, I have an arrow. That means that as I go left forever towards negative infinity, my function is going up forever towards positive infinity. Remember, f of x is the same thing as y, and that's describing up or down. So as I go left, I'm going up. All right, left, up, left, up. On the right side, I'm not going forever. I run into a point. When I start going to the right end, I hit a point. I have to describe that point. Well, that point has an x value of 0 and a y value of negative 3. So as I travel along this function to the right, I'm getting closer and closer and closer to 0 comma negative 3, an x value of 0 and a y value of negative 3. And that is it. We've listed all of our transformations, all of our characteristics, and we've got a graph to go with it. Up until this point, we've only been looking at square root functions. I'd like for us to look at a few examples of a cube root function. They look a little bit different because we don't have the limitation of not being able to have negative values underneath the radical. You can have a cubed root of a negative number, and because of that, when we go to our graphing calculator to get that list of x's and y's, we actually are going to have x and y values possible forever from the left to the right. There won't be any x values that we cannot use on this function. So let's choose a few of these that seem like they're going to be easy to graph. -8 comma -2 right here. -1 comma -1. 0 comma 0. 1 comma 1. And 8 comma 2. Now these are all good points on this function because the cubed root of 1 is 1, and the cubed root of -1 is -1. The cubed root of 8 is 2, and the cubed root of -8 is -2. So they show up on the graph. Now, I can add some detail in here. Maybe I do 5 and -5. Let's see, -5 comma -1.71. About right here. 5 comma 1.71. About right here. Get a little bit more detail. But I'm going to ask in a minute for the starting point. And technically, this function doesn't have a starting point. It goes forever in both directions, but there's kind of like we call an inflection point or an important point on this function where the behavior kind of changes, right? We want to consider that to be our starting point. It's still in the middle at 0, 0. From that point, we're increasing very slowly and decreasing very slowly to the left. We're going to get the best curve that we can through there. So that's that freestyle swimmer that we talked about in a previous video, that the head of the swimmer, think of that as the starting point. Now this function, is it increasing or decreasing? Well, it's got an arrow on the left at -infinity and an arrow on the right in positive infinity. As I'm traveling along, it seems to be always increasing, forever and ever and ever it's increasing. So I want to indicate that it's increasing from -infinity to positive infinity. Now we get to domain. There's an arrow down, and I'm sorry, we're talking about domain. That's left and right. There's an arrow on the left and an arrow on the right. So there are x values forever in both directions. -infinity to positive infinity are all real numbers. For the range, there's an arrow down. There's an arrow up. In both directions, we're going forever. So we're going to say from -infinity to positive infinity for the range of this function. And for a cubed root function, these are going to be your intervals of either increase or decrease, domain and range every time. It's always going to happen. Okay. Is there an absolute max or min? Well, there's no highest point, there's no lowest point because of those arrows. So in this case, there is not an absolute max or min. Now we get to end behavior. Think left and right. On the left, we are going down. Left is -infinity. Down is -infinity. So as we go towards -infinity on the left, our function approaches -infinity in a downward direction. On the right side, as our function approaches positive infinity on the right, our function is increasing or going up forever towards positive infinity as well. So we have positive infinity and positive infinity in our end behavior. And this is our end behavior. With cubed root functions, we don't have to think about approaching a point. We're going to go forever to the left and right. We've just got to decide, is it up or down? And if this is reflected across one of the axes, things could change. All right, let's get one more example. In this example, we have f of x equals negative cubed root of x plus 1 underneath the radical and then -1 outside of the radical. Now, let's review some transformations before we begin drawing on this graph. A negative in front is outside of the radical. That is a reflection across the x-axis. And remember I said outside, it's up and down. Well, if you reflect across the x-axis, you're going up or down. I told you might remember this by thinking of this negative has x escaped from under the radical x-axis. So we want to list out that transformation. It reflects across the x-axis. So that one's taken care of. Underneath the radical sign, we have a +1. Remember that underneath the radical is left and right. Transformations that are horizontal in nature. And it's always the opposite of what you think. So remember the coefficient in here is kind of weird when we think of it's really the reciprocal nature. We don't have an example here, but we do have this +1 under here, and that's a shift left or right. But it's to the left, which is kind of opposite of what we want to think is happening here. It's a shift left 1, and we just have to get used to that. And then we also have the -1 outside, and those are transformations that are vertical or up and down, and this one is a shift down 1, and those happen exactly the way that you think they should. So we're going to shift down 1. So that means that, remember, we think of it as a starting point, but really it's that point in the middle of this swimming function. And it's going to be shifted left 1 and down 1. So when we go to our graphing calculator, what we should notice is that the head of that swimmer is right here, and everything kind of increases and decreases to the left and right of that point. That's the middle point. Okay, that's the starting point. I'm predicting that when we graph it, it's going to be -1, negative. Well, let's see, I've got my calculator output here for a whole bunch of points that we can use, like -9, +1. And I'm looking for those easy ones to plot first. -2, 0, -1, negative. That's where I predicted it would be. -1, -1. And we got 0, -2, and 7, -3. Those are the ones that are easy to point. Maybe we could put a few more in here that are just kind of along the way so we can get an idea. Like -7, 0.8. It's about right here. And -5, 0.58. It's about right here. Maybe 2, -2.4. Right here. Let's go to 5, -2.8. So we can get a little bit more detail, but you really start to see as you try to sketch these things that, generally speaking, they are not growing or increasing or decreasing very quickly. The rate of change is very small along this function, except in the middle, except right here, close to the swimmer's head, if you want to think of it that way, the starting point. Is this function increasing or decreasing? Well, on the left to the right, it's constantly going down, 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 down. That's decreasing forever. Our domain, again, -infinity to +infinity, left to right. Our range, we have an arrow down and an arrow up. Now, so this confuses some of you because of where on the graph these arrows are, but you have to think bottom to top, not left to right. Bottom, arrow down. Top, arrow up. That's -infinity to +infinity. These intervals always have to be from least to greatest. You can't switch the order or you could lose some points. Again, since we have arrows in both directions, we have no absolute max or no absolute min. Those do not exist on this graph. All right, end behavior. On the left side, we are going towards -infinity for x. That's left. Left is x approaching -infinity, and this happens to be going up towards +infinity as we go to the left. On the right side, as we go towards +infinity for x, as we go to the right forever, going down forever. So the function is going to be approaching -infinity. Well, I hope that that is enough examples to get you started on how to graph and talk about some of these characteristics. But before we end today's video, wanted to quickly review how to write an equation of the radical with the given transformations. Okay, so a lot of times what I do when I'm doing this is I go ahead and do my f of x equals, and I give myself a little bit of space, and I go ahead and draw my radical, give myself some space under there. And then I start adding some things in. Now it says compressed vertically. Vertically is up and down by 1/3. That happens outside the radical at the beginning. Compressed vertically by 1/3. It's just going to be a 1/3 at the very front. Stretched horizontally by 5 is a left to right. Now that's going to be under the radical, and it's always the reciprocal of this number. So if it's stretched by 5, that means the number I'm going to have it inside is the reciprocal of 5, or 1/5. All right. Reflected over the x-axis has escaped. That's outside. That's -1/3 at the beginning now. Left 6. Actually, I should go ahead and put my x in here. All right. Now left and right is underneath the radical. That's horizontal. Left 6 is going to be a plus 6. Remember, it's always the opposite of the direction. So left 6 is towards negative 6, but we put plus 6 in order to get there. And then outside, we're going to do the up 17 as plus 17. And this is after the radical has ended. You know, some students put a little down tick here to show that it's ended. And this is our answer. We've got to be good enough with our transformations to know where things go. And the only way to do that, if you don't have your notes out, is to try to think of things underneath the radical being different than your brain wants them to be. You have to use the reciprocal for the stretches or shrinks, and you have to use the opposite direction for the shifts left and right. And then outside of the radical is going to be all of the horizontal, or I'm sorry, and outside of the radical is going to be all of the vertical transformations. That would be shifts up and down, and that would be stretches up and shrinks up and down. So a stretch or a compression or a shrink would be out front, in front of the radical. Up and down shifts are going to be at the very end. Now for the negatives, I just use, I've escaped for reflections over the x-axis, or why am I in here for reflections over the y-axis. Why am I in here? Escaped, to remember where those goes in. Once you get it pretty good, these questions are very simple. You always get them right. Well, that is it for today. I hope that you've been able to make sense of all of these characteristics and graphs, and I will see you in class.